All right. I guess we are live. Hello, everyone, and hello, Andy. Hello, all who have joined in live here, and welcome to our webinar: Analyze Your MUT Design with Cloud-Based Multiphysics Simulation. Since not everyone is as timely as you, valued listener, let's just take a 1-2 minutes maybe to fill in the room with whoever is planning on coming in live, and before going into the actual topic of today. So, how are you doing, Andy?
I'm good, Yuka. How are you?
Fantastic. Really looking forward to this event. How about you?
You've been quite excited about some of the things you've been seeing, haven't you?
I have. I just know that there will be some quite dazzling slides that you'll present. Some very interesting results, and can't really wait to go into those.
Yeah, it's something that I think everyone in the technical team in Quanscient has been quite excited about uh, sharing, and I've been looking forward to talking more about it. It's been a very, I would say it's been a huge area of interest for us, particularly over the last maybe 12 months or so. Um, so yeah, it's good to be able to talk to audiences like this about it.
Yeah. So without further ado, I guess most people who are planning on joining are would be around here. So again, welcome everyone to our event. So we're talking about analyzing your MUT design with cloud-based multiphysics simulation. So my name is Jukka Knutinen. I work as the head of marketing, and with me here I have our UK director and co-founder, the great Dr. Andrew Tweedy. Uh, so before going into the more introductions and whatnot, there's some couple of important housekeeping items to go over. So first of all, I'm sure as we move along with the presentation, there will be questions, and those questions are welcome at any point during the event. So in the top bar, you will see this questions tab. So whenever you have a question, just type it into the questions tab. It will come visible to only me and Andrew here, so we can basically address your questions at any time during the live event. So you can consider that as a sort of a throughout, so a continuous Q&A session throughout the event. So whenever you have a question, type it in the question chat and we'll take care of it. In addition, we do have a dedicated Q&A session at the very end. So yeah, at which any point you want to just type it in. Another thing, so as you will see, there is a materials tab also in the top menu. I guess it is in the top menu for you guys as well. So I will be dropping some materials there, some PDF handouts during this live event. So you can download them there when they are available. And I'll be sure to make them available, and I will be sure to tell you what those PDF documents are in just 1 second. So who are we? So as said, my name is Jukka Knutinen. I work as the head of marketing. So basically the marketing department. Not much of more to say about that. What you are probably more interested about is our technical speaker, UK director, co-founder, Dr. Andrew Tweedy. Would you mind telling the audience here a few words?
Of course, Yuka. So my background's primarily in ultrasound. I graduated with an engineering doctorate at the University of Strathclyde in their Centre for Ultrasonic Engineering. And I've worked for a series of ultrasound-based startups, initially working on designing and manufacturing ultrasonic phased arrays, and then getting increasingly into the simulation side of the industry. I was previously a co-founder at OnScale, and now I'm responsible for growing our UK office here in Glasgow. I hope you can't hear the rain on the window above me. December in Glasgow. Um, so yeah, this is an area that I have spent a long time in, and as I said earlier, I'm pretty excited to talk about.
All right, thank you. So quickly, we'll go through what we have planned for you guys here today. So after I'm done with these welcoming words and the housekeeping items, and actually this agenda itself, we'll do a very quick introduction to Quanscient also for those of you who don't know anything about it. But after that, I'll officially hand it off to Andy here, who will go into the actual topic itself. So, would you actually like to summarize yourself the main points that you'll cover here? So, we're talking challenges and then some live demos. Anything you want to say about these?
We're going to start off with a general summary of some of the challenges. MUT simulation has historically been very
Can you hear?
difficult. So the challenges as we see them and how we're addressing them in Allsolve, and then go on to give some really a worked example or a case study, if you like, with PMUT, along with a demo, before touching on some of the areas in CMUT that make them challenging. And then we'll wrap it up at the end with some technical questions.
That is exactly what we'll do. I hope, by the way, my internet connection isn't too wobbly. There might have been a
It
slight.
it wasn't great
Few
there,
sec-
but you're back.
All
So
right.
let's hope it stays like that.
Let's hope it stays like that. So, indeed, plenty of time for the questions at the end, and just a 5 minute conclusion, key takeaways after that. Now, before, as said, giving a very brief introduction to the tool we are going to be using for these case examples and the live demo, just curious on how many, basically, like how familiar are you with quant science? So I'm gonna just launch this poll right here. Give you guys 60 seconds or so. So yeah, judgment-free question. Just how familiar are you with Quanscient? Is this your first time ever hearing about us, or have you been a long time follower in our journey? Just to sort of calibrate on how deep to gauge into our history. Don't worry, not gonna bore you with those details. Just curious.
Yeah, we promise there's not going to be too much audience participation. I know in potentially people's last working week before a holiday, that's maybe not on your agenda. So it'll mostly be Yuka and I doing the work.
Yep. So just 4 more seconds for those who haven't responded, who still want to. We'll close out the poll. All right. Thank you, everyone. We can even take a look at the results here. So it's a mixed bag. For a couple, it's the first time. That's completely fine. I'm glad to have everyone here, no matter of your response.
A
So
broad demographic.
yes. So, a couple words on the handout. These are the documents that we'll be handing out to you. So, first would be about this API summary that we did a couple of months ago. So, basically, a PDF summary of this API webinar that we had. Uh, would you, Andy, just have a couple words on the relevance of the Quanscient API in ultrasonics, in PMUT, CMUT work?
It's a really unique feature of our tool, Yuka. Allowing a powerful multiphysics FEM solver like this to be plugged into user workflows is really quite unique. And I know that when we're talking about MEMS applications, often those workflows are indeed predefined in user organizations. So that ability to potentially start in our web-based tool and then take what you're doing and plug it into some of your existing tools through an API is relevant for a wide number of areas that we're involved in, and I would definitely say that MUTs is one.
Perfect. So, as a reminder, we will be handing out these in the materials tab later in the show. And the other one is actually just a PDF summary of our previous PMUT PMUT webinar that we did for IEEE, actually, with our CTO and co-founder, Dr. Alexander Hallback. So, for you PMUT enthusiasts, we will have something for you also there. Now, as promised, Quanscient also a cloud-based FEM multiphysics simulation platform, short and sweet. It's developed by our company Quanscient, established in 2021 in here Tampere, Finland, but has roots of more than 10 years of academia, basically through our CTO, Dr. Alexander Hallback, who developed this open source code library called Sparse Lizard that the software or platform is built upon. All right, so we have companies already using it in both industry, academia. Here are some of the happy customers who are already solving cloud-based simulations with Allsolve. Now, how I would like to summarize the benefits of the cloud-based nature of the tool is basically in 4 points. So first would be the speed. So basically just these reducing the runtime of large simulations from literally weeks to hours and days to minutes. And this is basically enabled by the next to unlimited computing capacity and RAM provided by the cloud-based nature of the tool itself. So instead of it being solved on your computer with limited computational capacity, it is solved in the cloud. Now, another thing is the scalability. So basically thousands of simulations in parallel. So you can run as many simulations basically as you want at the same time. Enables optimization studies, parametric sweep, manufacturer-aware design, a lot of which Andy here will cover in specific for ultrasonic use cases for PMUTs, CMUTs today. Also, the flexibility, more on the sort of Quanscient specific benefits. So no hardware investments. That is a cloud-based tool. All the physics and features are always included, so no modules or anything like that. There's an unlimited users with every plan, so no license restrictions either. Sharing a project as easy as sharing a link. And well, then the Python scripting interface. Don't know, Andy, if you're going to touch on the Python scripting interface today, but that is something that many people have found very cool. Well, we'll see if you go there. Then there's the usage-based pricing, but you can hear more about that perhaps in the Q&A session. Final thing was actually about the automation that Andy already touched. So basically through the API, there is the programmatic control of the simulations, which you can basically use to build these proprietary design workflows and in essence remove lengthy manual setups and repetitive tasks. Now, finally, before handing officially off to Andy and stopping my blabbering here, I would actually like to give you the executive summary right away. So I will be uploading it to here in the materials tab right away. Just give me 1 second. It's uploading it there now. So just again, it is now officially in the materials tab where you can grab it at any point and it will stay there to the end of the webinar. And as a reminder, we'll be uploading the previous PMUT webinar summary as well later in the show. Now, that's it from me. Without further ado, the stage is yours, Andy.
Thanks very much, Yuka. So I think I touched on this at the start as people were joining, but I'm going to start off with a little bit of background on the challenges of simulating MUT with traditional FEM tools. My main focus today is going to be on some pretty large-scale PMUT simulations, along with a live demo. And then we'll touch on some specifics of CMUT design, what makes them potentially even more challenging, how do we deal with those challenges in Allsolve with our quite unique range of solvers, and then we're going to do a little bit of Q&A before wrapping up. Now, I believe with all his wonderful tools that he has within GoToWebinar that Yuka is able to share a poll with you at the moment. So before I dive into the first few technical slides, we've got a couple of questions that should pop up on your screen. So, do you currently use a simulation tool for designing MUTs, or is this something that's new for you?
Yes, the poll is available now on the screen. So just let's take a minute or so just to give everyone time to answer.
So we've got a good distribution there again. A lot of people who are already running MUT simulations and potentially some people exploring it for the first time.
Right, 10 more seconds before we can show the results, show the distribution. All right, hope that's everyone who wants to answer. Yeah, there we go. This is what it looks like. So 63% says yes, 38% says no.
And do you have another one that you want to do, Yuka?
Yes,
Yes.
there we go.
Enthusiasm for polls. So yeah, this was a question that was in my mind, and Yuka and I talked. We thought it would be interesting to explore this before going into what I'm going to show you. So when you run these simulations, if you're one of the people that said yes, do you run simulations of just one cell or potentially pretty large arrays? And I think that feedback probably fits what we see when we speak to customers, that in other tools, most people are running relatively small scale simulations. We know it's a challenging area. That makes sense. But there's a couple of people already exploring some larger array sections, which should mean that what we're talking about today is very relevant.
All right, so that's already a minute. I hope everyone has again had the opportunity to answer. I'll end the poll and share the results for everyone to see. Here's how the distribution looked this time. Just as a reminder to you, Andy, the audience can see the live results. So here they are presented.
Cool. Yeah, good
All right.
distribution there. Right. Will we get into the main part of this? So, as we've discussed already, challenges in MUT with traditional design tools. So, I expect from our Q&A and polls so far that quite a few of you are experts already in this area, but I'm loath to give a webinar like this without any context at the beginning. So why MUTs? Why are we interested in them? I particularly liked this IEEE Spectrum article earlier this year by Professor De Gerken at Georgia Tech, just summarizing some of the history of MUTs and where they're going to now. And these couple of images really jumped out for me as I was flicking through that. It made me reflect on when when I was coming into the world, this was in the early 80s. This was probably um, the level of ultrasound technology that existed at that point. Very bulky, very expensive machines with very limited capability. This is where we've reached in 2024, and both from this article, I should add, and the compact, really beyond compact, I would say, capabilities that have come to ultrasound in recent years have really been driven by the development in MUT technology. So what we're talking about here is relevant. People are doing real things with this technology. So why is it a challenge? Well, we're talking about highly complex MEMS sensors, a lot of very detailed small structures. The arrays themselves are, albeit they may be 64 or 128 addressable elements, the actual number of cells within that can run into the thousands. And as a result, these simulations can run into tens or even hundreds of millions of degrees of freedom. It's beyond the scale of what's typically attempted in traditional FEM packages. The devices are broadband. It's one of the attractive aspects of the technology. So it means that transient analysis is very relevant, but as we know, that's a relatively expensive technique. They're inherently multiphysics, obviously with some differences between PMUT and CMUT. And there's many innovative structures being explored. We're starting to see work, a lot of work towards creating more broadband devices. Here's an example that we see from time to time in PMUT, where we have multiple different diameters of cells, and that brings in its own complexities for the simulation. And then finally, we'll touch on this in more detail later, but CMUTs introduce their own complexities, in particularly the non-linearity of the device. So this is not going to be a phased array design course. We're going to try and keep this fairly high level and light, but I wanted a couple of slides just setting some context of why I'm using some of the simulation structures, some of the approaches that I'm showing you. So if we think about the general topic of diagnostic imaging, and if we think about a linear phased array, we've typically got an arrangement of 64 to maybe 256 elements. And there's a few technologies that could be used to create an ultrasonic array of this sort of layout. We've traditionally used 1,3 piezo composites, which is where my initial background was, or we can now create MUT structures, right? So these could be CMUTs or PMUTs. They could be various different arrangements of cells in order to populate these elements. We've got different structures here which offer differing advantages in terms of layout, fill factor, potentially broad band, and even the shape of the cells can vary: rectangular, square, oval, circular. There's a huge range. So there's a lot of variation there. But as we know, there can potentially be thousands of MUT cells within a phased array. So how do we approach that? It's not traditionally been possible to simulate large sections of these arrays. So we typically start in simulation with what might be called a unit cell, the smallest little section that can be tiled out that somehow represents a section of this full array. And that can give us some good fundamental ideas of we might call it the acoustic stack, the design, the fundamental design of the membranes and the transducer layers. When we move on from that, we can go into various cross sections here. So we've got an elevation cross section, essentially a model of a whole element, or potentially using symmetry, a half or a quarter of the element. Or we can go in the other direction and take a cross section along multiple elements of the array. So we might talk about an azimuthal cross section. And these are good. Each of these can get us good estimates for beam patterns in the particular cross section that we've built the model. But ideally, to consider the full structure and the ultimate performance of the array, we really want to simulate large 3D cross sections. So ideally, we want a package that can allow us to progress through this series of models, building up in complexity, potentially running thousands of designs at the simple stage before we encounter very large models and therefore longer computational times. So a little spoiler, I thought you might have been listening for 15-20 minutes by this point. So this is what we're building up to, a full section with over 700 MUT cells in an array. We've excited a central element here. You can see crosstalk moving out. So that's what we're working towards. That's what OnScale enables. But let's look step by step at how we get there. So I'm going to focus on PMUTs to begin with, and I'm going to use this paper from Professor Horsley's group over at BSAC in Berkeley, which I've used before as an example. It's an array that was originally designed, the paper was written around fingerprint sensing. But what we're going to do here is look at this array as if it was a linear array for diagnostic imaging. And we're going to pull out some of the things. We're going to operate it into a water load. And we're going to pull out some of the things that we would be interested in if this was a diagnostic imaging linear array. So as I mentioned a couple of slides ago, the simplest model we can construct is what I would call a unit cell. So the smallest little section that we can tile out to create an infinite array of PMUTs. And that's what we've got on the screen here. So we've got a representation of the PMUT structure that we saw on the previous page, where it's got a silicon oxide carrier structure. It's got an aluminium nitride piezo layer and a silicon membrane on the top, and we're operating this into a column of water. So it's a very simple model. It's got symmetry applied along the red dotted lines, but we can get quite a lot of good fundamental information out of it. So we're going to run some transient simulations on this to show some of the basic performance. Now, before jumping into that, it's difficult to talk about finite element analysis without talking about meshing, everyone's favorite subject. And I promise this is going to be the only slide that I show any meshes on. So I wanted to show this basically to demonstrate that there's a huge amount of flexibility in Allsolve's approaches to meshing. We can have structured meshes, we can have unstructured meshes, we can have hybrid approaches. We can refine different areas of the mesh. Ultimately, it comes down to your requirements. The best advice I can always give on meshing is build a simple model like the one we have here and run a mesh convergence study. Pick the outputs that you care about, see how they converge with meshing, and that allows you to choose the right mesh for your device. So we're going to excite this model. It's going to be a transient simulation. We're going to excite it with a short voltage wavelet, and we can observe various things happening in the model. So the first thing that we'll get is we'll see this is the current, and if we look at an animation of the field outputs over time, we'll see that we get some displacements in the membrane itself, and we'll see that we observe a pressure wave traveling out into the water column and being absorbed at a PML at the base. Now, I should have said a couple of slides ago, I've oriented all the models in this slide deck in the same way, and I've got them with the waves propagating down the way. And the only reason for doing that is that it's a little bit easier to see the MUT structure and the load in one view. So that's the reason for doing it. I hope that doesn't confuse anyone. The two graphs that we've got to the right here are the surface displacement at the center on the front of the membrane. So we can see the pulse ringing down here. And then further out, we can see the pressure in the water column, I think about halfway through the load here. So we've got about a 50% fill factor here. We're probably not into the near field zone, sorry, the far field zone here. We are still in the near field, and I think we're seeing some effects from that. Worth pointing out that this is a trivial model to execute. We've run this for maybe, I think, 15 cycles at the center frequency. It's got about 35,000 degrees of freedom, and we've run it on a single core in less than a minute. So very low cost model. It's a model that as a designer, I would want to run potentially thousands of times in large design studies, sweeps, potentially optimization studies. So it gives us a lot of flexibility there. So, okay, we've run a unit cell model. We've got some confidence that we have a reasonably wideband device that's operating at our intended frequency. What do we do next? Well, it would be nice to see what the elevation beam pattern, so some might say the vertical beam pattern from our intended array. So the array that I showed from the paper had 56 elements here. I think the way I've done it, I've actually simulated 55 because I've got symmetry in the center here. So we've basically patterned out the design for a number of elements. We've got symmetry through there, and we've got a plane of symmetry running down either side of the model in X. And what that does is it creates an infinite field of these elements. We're going to drive the whole element here. And what that's going to let us get out on top of what we had before is the beam pattern and potentially the electrical impedance of the element. I've not shown that here. This design isn't particularly resonant, so there's not a huge amount to see in the impedance plot. And we're going to do that in this case using a harmonic solve. That will give us the CW displacement and ultimately beam pattern from this element. And that might be as often a convenient way to measure in practice. So here we can see the surface displacement and acoustic pressure in the load, CW at, I should have mentioned on an earlier slide, the design frequency for this device is about 15, 16 megahertz. So we've driven this at 15.8 megahertz. And we've got a nice elevation beam pattern here, very narrow because it's quite broad in terms of wavelengths. And we were able to get this again in less than a minute. And even though it's starting to become quite a large simulation with a couple of million degrees of freedom. Okay, so we're starting to get a feel.
Sorry, Andy, just
Yuka,
to
you've popped
hop
up.
in for a second.
Go
There
for
was
it.
a question just a couple of minutes ago asking what change do you expect in far field compared to near field?
That's a very good question. Let's get back. The field would be much more uniform. If we look at the pattern here, you can see there's an interference pattern in front of the cell, and that's the waves between adjacent cells, which are of course surrounding this, interfering with each other. As we move into the far field, the field will be much more uniform, and I think you'd probably see somewhat less ringing on this uh, time plot of acoustic pressure. So those would be the two main differences that you'd see from this plot.
All right, and there was also a before letting you move on, there was another good comment suggesting to make the figure legends easier readability
The legends, yeah.
in the
I hope that
future.
you'll be able to read them
So
in more detail on the
thank you
handout,
for
everyone.
that suggestion. Truly noted here.
Yeah, that's appreciated. I realise that they're a little bit small on people's screens at the moment, so hopefully the handout will rectify that. So we've looked at this design through an elevational cross section. Let's do the same in
Yes.
azimuth.
So back to you.
Yeah, thanks, Yuka. So here we're taking a cross section as along X in our model, but in the azimuth direction. And the key use of this model is simulating crosstalk along the array. So we're going to simulate a driven element at the center, and in this case it's got half symmetry applied to it. We're then going to simulate passive elements adjacent to it, in this case another 6 of those, and we're going to observe crosstalk moving out. Now this is actually a point where I wanted to jump into Allsolve itself and do a quick demo. So as you can see, Allsolve runs in a web browser. So I've just flipped to another tab in my browser here, and I've got a model that I can manipulate. I've built this structure within Allsolve, but equally I could have imported that from CAD or GDS2 files. There's a lot of flexibility over how that's done. I'm not going to go into the model construction here. What I wanted to just highlight was in a PMUT, the different physics regions that we're enabling. So in the in the device itself, we've got elastic waves. We're simulating electrostatics and piezoelectric coupling within the aluminium nitride layer. And then we're going to have acoustic waves applied to the water load. We can quickly go through and look at some of the different boundary conditions. So we've got symmetry in X here. We've got symmetry in either side for Y. So we've got we're going to have in the elevation direction, we're going to have an infinite stack of elements. Excuse me. And we're one interesting aspect that I wanted to highlight here is that there are, in the paper that this is based on, we have the MEMS wafer bonded to a CMOS wafer through these little interconnects. Now, the geometry, the exact geometry of those aren't specified, um, but it brings up a very important topic, especially when we're talking about crosstalk of the boundary conditions, particularly at the rear of any MEMS structure, and how we impose them will have a big impact on the crosstalk that we see in the device. Now, for this simulation, what we've said, we've modeled some of the electrical interconnects, and we've imposed a clamped condition to the rear face of those. So we're saying that the CMOS wafer is rigidly clamping them. Now, what would be really interesting and might be work that we do in the future is to model at least part of that CMOS wafer and perhaps try to understand how big an impact that has on the crosstalk modes that we see. So that might be something that we do some work on in the future, and please let us know if that would be of interest. I'm going to move on to some of the simulation results because we've got quite a lot still to get through. So out of this is a transient simulation I've selected here from quite a long list of simulations that I've run. We can pull out things like surface displacement, acoustic pressure, the drive voltage that we've imposed as a boundary condition, and as I showed before, the observed current on the device. Or indeed, if we want to move across here and look at the fields on the device at potentially, let's say, the 40th time step, if I just rescale that, we can see quite a broad wave leaving the device here, some elastic wave modes propagating across the structure itself. This is the main driven element here. So it indicates to us that we're seeing some crosstalk. It would be interesting to find out a little bit more about that. So let's see if we can switch back to my slides now and look at that in a bit of detail. So crosstalk was one of the things that I pulled out of this model. What we're looking at here, I showed you the results of a transient solve. What we've got here is a harmonic solve at, again, 15.8 megahertz. And this shows us the crosstalk across the essentially 13 elements that we've modeled on a dB scale, and then the azimuthal beam pattern. So ideally, to recap, what we want is this to be a nice wide beam, and to a large extent we've got that, but we can see that the crosstalk indeed is having some sort of impact on it. We've got a bit of ripple in the beam. That might be something that is a problem for high fidelity imaging, for beam steering out to wider angles, and we might need to work on that to improve it. So even though we're running models that are still running in under 5 minutes on a single core, we're getting some really useful insights into how the device is behaving. So we've run unit cell, we've run cross-sectional models. I wanted to really demonstrate that what Allsolve can do at a larger scale. So this is a full 3D section of the device. We're going to drive, sorry, this central column of elements, and we're going to observe crosstalk moving laterally through the device. It's essentially a 13 element section of the array that we showed from the paper, with a column of 55 elements when you account for symmetry. So symmetry considered, we're essentially simulating 715 cells in this device. Now, this is the drive voltage and the drive current. Those are things that we've seen before, so I'll skip over them quite quickly. This is the transient surface displacement on the center of the driven element, and this is the acoustic pressure, again, halfway into that load, so quite close to the front face. And you've seen a snapshot of this already, but this is an animation from the transient simulation of the full model showing crosstalk moving laterally away from the device, and the main element ringing down. So this whole simulation was executed in under 15 minutes. It's parallelized using domain decomposition across 32 cores. So even though for a transient solve, it's around a 5 million degree of freedom model, we can still execute it very quickly. And indeed, we could go larger if we needed to. We can do the same thing with a harmonic solve. I've got Yuka, sorry, jumping in for a question.
Yeah, sorry, I know we are sort of we only have 14 minutes left. We're sort of on the clock, but there were a couple of very good questions we could just quickly address.
Let's do it.
So first was that is this far field beam pattern made with an extrapolation based on the near field pattern?
It is made from an extrapolation based, yeah, that's a good way to put it. We basically sample the acoustic wave as it's leaving the device across a plane, and then we do indeed carry out a Kirchhoff extrapolation, so Kirchhoff's frequency domain integral to get far field results. Now we could do that. We could um, use Kirchhoff's integral to look in the near field as well. It supports that. I chose to do far field for this because it made sense. It kept things simple.
Perfect. One more question. By the way, just for to let everyone know, we will get back to you for all of the questions, all of the comments you leave here. So keep them coming, just so that we have time to let Andy finish his presentation here with this awesome stuff. I'll just ask one more question right now, which is that are these results from the software matching with the experimental data from the published research papers?
Really good question. The tests that we've done here aren't like for like with what was done in the paper. I've not taken the time to try and recreate. So in the paper, they were looking into a 250 micron PDMS load because they were trying to do fingerprint imaging. So they were trying to find an easy way of recreating the glass and polymer display stack that you encounter in fingerprint imaging. And PDMS was quite a nice. It's quite similar in acoustic impedance to tissue, so it was quite a nice way of doing that. What we set out to do here is more to do with diagnostic imaging. So the results are not like for like. They're operating into different loads.
Perfect. And as said, keep the questions coming. We'll address them here either live or just get back to you with an email, even if we don't have the time to cover all of the questions here. With that said, uh, please proceed, Andy, and thanks again
Yeah,
for all the
we'll
questions.
see how many we have time for at the end. So yeah, this is I showed you the transient results, and then this is a harmonic simulation at 15.8 megahertz, giving you a picture of the crosstalk. So in reality, we should expect the cross-sectional models to do quite a good job here. We've seen some small edge effects at the edge of the wafer here, but other than that, it's fairly uniform. What this does illustrate, though, is we could start to consider much more complex designs where potentially the MUT geometry itself changed throughout the elevation of the element. So it brings in a lot of flexibility. We talked a little bit about what went into these beam patterns. So these are the beam patterns from the full 3D section. Because of the uniformity that I just spoke about, they are actually very similar to the cross-sectional results. But as I said, we now have the freedom to consider much more complex designs that maybe don't support the sort of symmetries and the sort of uniformity that cross-sectional models would completely capture. So that is what I had to cover on PMUTs. I wanted to speak a bit about CMUTs as well, but what I didn't want to do was go through really the same process again with a CMUT design. So really what I wanted to focus on here is what's different and how do we tackle that. So there's a lot of similarities. CMUTs are still MEMS devices. We can still use some of the same simulation strategies that I've just covered, but we've got different physics to consider. We're considering electrostatics rather than piezoelectrics. We've got biasing, we've got non-linearities to consider. Potentially, if we're operating in collapse modes, we've got contact conditions to think about. So all of these brings in layers of complexity. So similar to what we did in the previous slides, I wanted to start with a reference from the literature. So this was some work that I was involved with back in 2016, 2017 with the team at DTU Nanotech in Denmark. We did some work on various CMUT designs, and this was quite a simple design that we used to look at pull-in curves. We used to do transient simulations, and we're going to recreate some of that here, but also then go on to look at Allsolve's fairly unique multi-harmonic solver, and I'll talk a little bit about that in a minute. So Yuka mentioned sweeps earlier, and it's something that I usually talk a lot about. This is the only place I've used it in this presentation, but essentially we've got a pull-in curve showing normalized bias voltage versus normalized deflection, and we were able to recreate the results in the paper. We ran 200 static simulations in parallel and completed it in under 30 seconds. So a lot of parallelism and speed. We can then use these static bias points as a starting point for a transient simulation. So this is, I think this was about 50% biased to 50% of the pull-in voltage, and then we applied a short voltage pulse to the device. I didn't really get this animation looking very good, but I hope it illustrates what we were doing. And a little bit like the PMUT devices, this is a unit cell simulation. We've got displacement and pressure in the load. You can see, as is characteristic, these are extremely wideband devices. And then this is something that I wanted to touch on a little bit more. We have quite a unique multi-harmonic solver, which allows us to simulate non-linear effects across many different harmonic components, including in this case the DC bias. So here we have a simulation where we have the DC bias with all elements driven in parallel at the same phase. And then we have a simulation where we've applied some phase differences between adjacent elements, really just to illustrate the flexibility of that solver. It's a very powerful approach for situations where you have nonlinearities and potentially multiple drive frequencies mixing together. So it's a really good companion to the transient solves that we would typically do in CMUT. So I had to cover those CMUT slides quite quickly there. Apologies if that was maybe a little bit fast, but I'm glad we managed to get through all of that. So Yuka and I had wanted to have some opportunity for questions at the end. So I don't know if Yuka's still on. I know he was having. Oh no, there he is. He's here. I thought we could open the floor for some questions if there's any lined up or any more to come in. You're muted.
There we go. Thanks.
No
So
worries.
before going into the question, letting the floodgate fully open, well, actually, these questions here, so they are for you to think about, to sort of to take home as questions to think about yourself. So question for you guys would be, what would be the biggest benefit from being able to accurately simulate your MUT arrays, full arrays? And also, what is the most important effect or output you'd like to simulate but can't? So for these questions, you can either fill it in, you can answer it in the chat if you want to let us know, or you can just think about it in your head. And while you think about that, I'll just place this one last poll that we have here for you guys. So simply asking if sometime after the event you would like a live demonstration of what Quanscient also can do to your specific use case. Uh, just to explore Quanscient also a tad bit deeper to your specific use case. So since this hour is painfully short when there's a lot of interesting topics to cover. So if you're into it, we'd love to talk with you further, see what kind of a change all of the stuff that Andy has here been presenting. Just explore what can it do to you guys. So yeah, we won't be publishing these results or making these uh, viewed for everyone. So just have your say whether you'd like something like this or not, and we'll be reaching out to you. Someone from our team will be in touch with you. With that, I see we have just. I will, by the way, be closing the poll right away. Thanks everyone for your answers. Now at this point, uh, well, since we have 1 minute 30 seconds, after which the webinar platform will cut us short, like a dead stop. Uh, to conclude on my part on the practicalities, I will be sending out the speaker slides to you immediately after the event, and I will be also sending the PDF summary of this event along with the webinar recording to your email by the end of the week. So that's it from my part. And you have 1 minute, and also all of your questions will be answered to you by email later this week. Andy, there's 60 seconds. How would you like to conclude?
The 60-second sum up. Thanks, Yuka. Yeah, just look, thanks everybody for the time today. If I was to sum it up very succinctly, I would say that the capabilities that we have in MUTs are enabling MUT simulations at a new scale, and I think it really has the potential to not just increase confidence in designs and reduce physical prototypes, but genuinely speed up um, the progress towards market, reduce time to market for what are really incredibly complex devices. And with that, thank you for your time, and hopefully speak to you soon.
Thank you. Bye bye, everyone. Have a great day.